So, set theory. Okay. Um, so basically, um, we just want to learn the relations between sets. But first, we're going to talk about what is a set, uh, and then we're going to talk about some operations on sets. So, a set is just in English it's called a conglomerate conglomerate of objects. So it's just actually, it's just like a bag that which is full of objects. So you can put anything in this bag. Okay. Um, in also in math, a set can also be defined by describing the contents, what's inside the set, or by listing the elements of the set. Okay, enclosed in curly brackets. Okay, so you have two ways to describe the set. One is define, you know, by describing the contents. Uh, the second case, you want to list all the elements of the set um, enclosed with a curly bracket. This basically applies to certain type of sets that either it just contains a finite number of elements, or the elements which has certain kind of pattern. Um, Now the first case you just try to use probably like even the English language, you can describe what this set is supposed to be. So for example, um, so for example, so if we say we try to define a set of all prime numbers, the set of all prime numbers. So basically we use the first approach, right? So describe the set. We describe the set uh, by its contents. Now, in this case, it's hard to list the elements of the set if we say, oh, we want to define a set of all prime numbers, right? It's kind of tough to list all the elements. So this is just one way. Uh, and the other example is a set of all books written about the U.S. history. Okay, it's clearly defined, right? So if you go to library and if you take all the books written about the U.S. history, and then we can put all these two books together, then we create another set. Okay, so this way we can actually define a set by describing the contents. Now, if a set contains finite element, then you can define the set by listing all the elements. So, for example, this set contains 4 elements, so we can just list all the numbers, which is only 4. And the next set actually lists some cities in the world: New York, New York City, Boston, Austin, London, Tokyo. So this set is also actually this set also contains a finite number of elements. 1, 2, 3, 4, 5. There's only 5 elements. Okay. So we can define the sets by listing the elements. So these are basically 2 ways to describe a set. Now, it's always easier to use the diagram to describe a set or draw a set. Okay. So sometimes to solve the problem using the diagram, it will be easier. It just gives you some kind of overall picture of what's happening. Okay. So so let's say A is a set of students. Okay. It could be all the students in Fitchburg State University, or all the students in the graduate program in computer science. So it's a set of students. Um, and then we define B to be a set of female students. So then we can we can define the relationship between A and B, right? So so it's kind of clear, you know. So every female student is a student. So that means, so if you actually think about set of students as the circle, which I put A here, describe as A. And then if you actually describe the female set of female students as another circle, now clearly you can see that the B should be included in A, right? So just use our common sense or use our knowledge. Okay. So in this case, B is called a subset of A. B is a subset of A. And normally we use the notation B, I don't know how, it's just a subset, I don't know how can I call this. It's just like a U, just, put it upside down. Now, sometimes you will see that the B is a subset of A. We just use that notation, and sometimes we just put a bar underneath. So normally there's no much difference, but in certain case, people are gonna also include, in the bottom case, people also include the case where B is actually A. B is the same as A. So that means B is a subset of A or B. So including A. Now, in this case, sometimes people use that notation to represent the relationship between B and A, such that B is a subset of A, but B had, there are certain elements of A which is not in B. So that means sometimes it's called a proper subset of A. No. So we use that notation. So also, we're gonna actually use the notation called actually, to define the relationship between the set and the element of a set. Okay. So if John is a student, so that means if A is a set of students and John is a student, and then we say John is an element of A, because A is a set of students and John is an element of A. So we use the notation John is in A. Also, if Barbara is a student, and we can say Barbara is an element of A. And also Barbara is a female student. So we can also say Barbara also belongs to B. Okay, so this basically defines the relationship between two sets and the relationship between a set and an element of the set. Okay, so we use these notation. Now, so the first case we define a subset, right? So one is a subset of the another one. Now, there's another kind of situation that you can find two sets. None of the set is the subset of the other. Okay, but however, they share some of the elements. Okay, now this is called overlapping. Okay, again, we can define two sets. A is a set of students. B is a set of workaholics. Okay. Um, now let's see what's the relationship between A and B. Okay. So to find a relationship between these two sets, A and B, then we need to find out, how many students, students are actually in set A, but how many students are also in set B? Or on another way, we can think about a set B, so the set of all workaholics. And how many actual workaholics are also students? So these are basically the same question, but from this different perspective. So then we find out, some students are workaholics, some are not. And also among workaholics, there are students, but not every workaholic is a student. So in that case, then we can use the term overlapping. So that means A and B has certain common part, but A, is not a subset of B, and B is not a subset of B. A. So in this case, so we use the diagram, so we can draw the circle of A and the circle of B. And then sum of the A is also B. Okay, sum of the elements in A is also B, and the sum of the elements of B is also in A. So that overlap part is the student. It's both. Every element in here, is they are also they're either a student and also a workaholic. So both student and workaholic, they belong to that area. Now in this area, the Y area, so that means they are student, but not workaholic. And here, they're workaholic, but not student. So that's the only area that they are both student and a workaholic. So that's overlapping. Now that's the other relationship between two sets. Okay. Now let's take a look at the another scenario. These are called disjoint set. Okay. Now it's very straightforward if you look at the diagram, right? So A is over here, B is over here, and they don't overlap. So now it's easy to find some examples, right? Now let's take a look at the example of this. A is a set of people who support Red Sox, okay? And B is a set of people who do not support Red Sox. Now these are two group of people. They don't overlap, right? So now, if you actually define A as a set of people who support Red Sox and B as a set of people who do not support Red Sox. That means A and B has no common area. Now we're talking about, you know, about whether they support the Red Sox or not. We're not talking about people in A and B in general, right? So it could be like a people in A and a B. They both like a beer. They both like a drink. Okay. So, but that's not the point. The point is we define a set to have certain characteristics. So A is a set of people who support Red Sox or not support Red Sox. Now, if you divide the set in this based on this criteria, then A and B has nothing in common. So that's the point. So that's why we need to understand that the people in A and B might have something in common, but that's not the point. The point is, nobody can support and not support the Red Sox. So but in this case, it's called disjoint set. A and B has nothing in common. Now, if you want to see some other example, let's say A is a set of even number. And B is a set of odd number. Now, in this case, A and B are also disjoint sets, right? Do we have any other example? Like A is a set of all positive number. B set of all negative number. These two are also disjoint sets. So you can always find many examples that disjoint. Any questions? And now the next relationship is called equivalent set. Okay. So equivalent set is basically, so let's A be a set of numbers divisible by 6. Okay. And B is a set of numbers divisible by both 3 and 2. So we define two different sets, A and B. But if you actually study these two sets, and if you know a little bit about elementary math, we know that if any number that can be divided by 6, okay, any number which is divisible by 6, then that number is divisible by both 3 and 2, right? So, for example, if we talk about a number which is divisible by 6, so that number could be, let's say, could be 6, right? Could be 12. Could be 18. These are the numbers that are divisible by 6 because, it's actually kind of a multiple of 6. Now, if you look at further, if the number can be divided by 6, that means that number can also divide by 3, and this number also can divide by 2. Each number who is divisible by, by 6, then it can be divisible by both 3 and 2. So technically, set A and set B are the same set, right? So in this case, we call it these two sets are equivalent set. Does it make sense?
Yes.
Yes, yes.
Okay, let's move forward. So let's take a look at the following example. Let me actually erase this. Okay, let's just okay. Let me first actually take away all these things. Okay. Now let's take a look at this example. So we define A to be let A be a set of New England Patriots fan, and B is a set of New York Jets fan, and C is a set of Boston Red Sox fan. X, it looks like a big set, right? It's a set of sports fan, so looks like X is a set that includes all 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 the people who are sports fan. Now, can we actually draw the circles to illustrate the relationship?
X is a big circle and ABC are small circles inside X.
Okay, so let's say A is this. This is A, all the New England Patriots fan. Now, when I draw B, what do you think the B gonna look like? Is there an overlap, or B is a subset of A, or A is a subset of B, or
B is a separate one, so it doesn't interfere with A.
okay,
Overlap?
overlap. Any different opinion? I think this is kind of a tough.
I'm not sure I know of any New England Patriots fans that are New York Jet fans.
Yeah, that's a tough question. Yeah. Now, mathematically, if you say A is a set of New England Patriots fan, and the B is a set of B is a set of uh, you know fan that are not a New England Patriots fan. So if it's one is New England Patriots fan, the other one is a group of non-New England Patriots fan, Patriots fan. Then you can say there's a disjoint, right? But here, technically, I don't know. So you might be able to find a person who is a fan of both, but as Chuck said, it's unlikely. So I would say um, A and the B, they most likely they're they're disjoint. Okay. Now even if they overlap, I don't think the the overlap must be very extremely small. It's unlikely that you have a big overlap, right? But 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 I would prefer that they're disjoint. But this is actually kind of great. But what about C?
C also disjoint.
I think C could be like this, but probably going to be big overlap with A, but a small overlap with B, right? It's still possible for whatever reason. Some people they live in Boston, but you know, I don't know. So they could be a New York Jets fan and a Boston Red Sox fan. Could be, but again, so that's again another kind of things we can discuss. Normally people living in Boston, they most likely they're going to be both the New England Patriots fan and the Boston Red Sox fan, right? But there's a chance that some people live in New York, New York City. They they are fan of New York Jets, but probably they moved from Boston. So um, they could be a Boston Red Sox fan as well. So I would say more likely C gonna overlap with both A and B. Um, now, what about X?
X is a big circle. ABC fall inside X.
X gonna be something like this, right?
Yeah.
So A is a subset of X, B is a subset of X, C is a subset of X. Everyone who actually like sports, they um, should be an element of A X. Okay. So that could be like likely the case. Um, now let's actually talk about even an easier case. The previous case is kind of there's still some gray area. Even though it's likely that the Patriots fan is not gonna be a Jets fan, but in this case, it's pretty clear. So A is a set of people who speak English. Okay. B is a set of people who speak French. There could be some overlap, right? No question about it. And the C is a set of people who speak Spanish. Okay. And X is a set of people. So now if you take a look at this diagram, now these are the group of people who can who can speak English only, right? And these are group of people who can speak French only. And these are a group of people who can only speak Spanish. Now here, these are a group of people who can speak both. They both belong to A and they belong to both A and C. So that means they can both speak English and Spanish. Okay. And here, they both belongs to both B and C. That means they can speak French and Spanish, but not English. And here's English, Spanish, but not French. And this group of people who can speak both English and French, but not Spanish, right? Now, the center part, these are a group of people who can speak all three languages, right? So I think that if you use the circle, use the diagram, you can actually easily draw the relationships. So this is actually it, you know. So when you actually draw this, you need to check whether A, B, and C are a subset of X. Yeah, that's true. So we did that one, right? There are people who speak only English. Yes. There are people who only speak French, speak only Spanish. There are people who speak English and French, but not Spanish. English and Spanish, but not. Oh, I'm sorry. That's not English and Spanish, but not French. Oh, I'm sorry. It should be French and Spanish, but not English. Oh, I, 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 I messed up. You know, I think this is not likely the case. Okay, so English and Spanish, but not French. Okay, and last case, English, French, Spanish, French, and then English. So that means French and Spanish, but not English. Okay, yeah. And there are people who speak English, French, and Spanish. Yes. So this is actually the perfect, you know, diagram. So basically, it illustrates the relationship among these four sets. So now let's actually focus on the elements and the sets, and we find the relationship among them. So we know that we can write X belongs to X if X is an element of set A. X belongs to A. So if A and B are two sets, and A is a subset of B, so then we can say if for every element of X which belongs to A, it is true that the X also belongs to B, right? So that it's also basically it means that if A is a subset of B, so that means all elements of A are also in B. Okay, but not necessarily vice versa. Okay, if all elements of A are also in B, A is a subset of B, but not the other way around. It could be the other way is also true. In that case, A and B are equivalent, right? If all the elements of A are also in B, and if all the elements of B are also in A, then A and B should be equivalent. But at least if A and B are equivalent, then you can say A is a subset of B, that's correct. And B is a subset of A, that's also correct, right? But if both are true, then they should be equivalent. A and B intersect if there are X, such that the X belongs to both A and B. So that means it's pretty simple, right? If A and B intercept, so that means there's always some element which belongs to both A and B. If you cannot find such an element which belongs to both A and B, then you can say A and B are disjoint, right? Otherwise, you can always find the X. So this is also a very straightforward. And also, the third proposition is A and B are disjoint if there are no X such that the X belongs to A and the X belongs to B. So that means A and B has no common element. So you cannot find any X that the X belongs to both A and B. So if X belongs to A, then X definitely not belong to B. If X belongs to B, then X definitely does not belong to A. So there's no common element. So if A and B are equivalent, then if for any X, if X belongs to A, then X belongs to B, and vice versa. If X belongs to B, then X belongs to A. So which means that they have exactly the same elements. So you can always say if A then you can say A equals B, right? So these are the 4 propositions. You can basically define the subset, intersection, and the disjoint sets and the equivalent using the elements of sets. Now, in math, when we talk about a set, okay, then we basically talk about, the elements of a set. Now, there's one particular set, okay? So,
Excuse me,
yeah,
Professor. I'm
yes,
sorry to interrupt, but one of my friend is not able to join the class. Her name is Stravani Waka.
he's not able to join the class. Oh, I don't know. I just actually set yeah, I allow everyone to join, but yeah, I just did. Sorry for that. I thought I just did, set up the setting in the Google Meet so everyone can just join without my permission. Okay.
Thank you.
Yeah. So so we will use one particular character U to represent something called a universal set. Okay. The universal set basically is basically defined as the set of all objects. Okay. Now, the universal set, we define the universal set. It basically is defined as all objects, under consideration. Okay. Or all objects. So in our area, in our domain, in the topics we just talked about, Otherwise, the universe set, if includes all, then you can say the universe is the universal set. But we're not talking about this. We're talking about all objects under consideration. For example, if we talk about all the students in Fitchburg State University, then we can say the universal set U is the set of all students in Fitchburg State University. Okay, so that's the universal set. Or if we talk about all the people in the United States, then the universal set is a set of all people, the people in the United States. Okay, and then we can talk about the set of all people in Massachusetts, the set of all people in a set of people in Rhode Island or in different states, or even in Boston. So we gonna, when we define the universal set, it's basically the set of all object of interest. We're interested in. Now, suppose U is a set of all people. Obviously, any set of people is a subset of U, right? Okay. So, like I say, if we define the U, the universal set, as the set of people in a set of students in Fitchburg State University, then then we can say any set of student in computer science, and this set is actually a subset of the universal set, and the set of student in English department, then that's also a subset of U. So let's take a look at another case. Let's assume A is a set of children, probably a children in certain in a particular city or in a particular group. Okay, and B is a set of senior citizens. Okay, so A and B are disjoint. Okay, so now what is the universal set? So in this case, the universal set should be like a set of people, right? Because both actually children and a senior citizen, they don't exhaust you as they are adults who are neither children or senior citizens. So you can say, when you talk about a group of people, you cannot say, oh, they're either a children or senior citizen. That's not the case. There are always people like adults. They're neither actually still children nor senior citizens. So in that case, if you use the circle to represent the relationship, then you can say A is here and B is here. B is a senior citizen, A is a children. Okay, but there are still actually many. This is a universal set U. So there are still actually some elements that they don't belong to A and B. So there could be some other. Okay. And also, if A is a set of people who are US citizen, if we define the set A as a set of people who are US citizen, B is a set of people who are not US citizen. Now, in that case, okay, now if we define U as set of people, okay, so U as a universal set, it's a set of people. Then it's clear that if we define A is a set of people who are US citizen, so that means A is a subset of U, right? And also B is a set of people who are not US citizen. B is also a subset of U. Now, if we actually put B and A and B together, do these two sets actually form the universal set? Let's say A and B, they're disjoint, right? A is a set of US citizen. B is a set of non-US citizen. Okay, so they don't overlap. But can we find any person who does not belong to both? So I'm gonna say, well, I'm not US citizen, so I'm not an element of A. But I also don't belong. I also don't belong to B. Does that make sense? If I'm not, if I'm not in A, I definitely going to be in B, right? So there's no actually choice. So you are either in A or in B, and no third choice. So A and B basically exhaust the whole U. So A and B put together, that's the universal set, you know. So looks like then you can say this is a universal set, and then I cut the universal set into half, and this is A and this is B, and there's no place for any other, case. So in that case, A and B exhaust U, and every person is either U.S. citizen, which belongs to A, or not, which belongs to B. So in that case, we say A is a complement of B. Okay, A is a complement of B. So we can write A as, A is a B to the C. B to the C, that basically the complement of B. Okay, so complement basically means the other side. Okay, so that defines the complements. And back to the second case, because you can always find people who are not in A and not in B. So we cannot say A is a complement of B, because if a person is not a children, this person may not be not a senior citizen as well, right? So it's not like if it's not a children, that the person must be a senior citizen. So then in this case, then A and B are complement to each other. But this is not the case. If there are people who, don't belong to A and B, they don't belong to A and they don't belong to B. So, but in this case, the second case, A and B, U.S. citizen, non-U.S. citizen, if they don't belong to A, and they must be in B. So there's no other alternative. So in this case, we can define something called a complement. So A is a complement of B, or on the other hand, you can say B is a complement of A. Either way, they're correct. Any questions on this? Okay, let's just move forward. So here's the definition of complement. A is a complement of B if A include all elements of U that are not in B. So A is a complement of B. That's U. A is a complement of B if it includes all the elements of U that are not B. So that means A is everything outside B, right? But still in U. Okay. So A and B basically, they basically A and B forms the universal set. So that's the definition of a complement. Okay. Now, one of the example, probably like 100 years ago, the answer is very clear, but now it's kind of different. It's a very sensitive topic. If A is all the female student in Fitchburg State, B is all the male student in Fitchburg State, then is A a complement of B? Probably the answer was yes, but now we don't know, right? Because we may have some third gender that they're neither A nor in B. So that's just get some sense of what the complement means. Okay. Let's take a look at the operations on set even further. Okay. Let A be a set of birds. B be a set of cats. Okay. So now if we're interested in relationships between A and B, and then we would say they don't have any common elements. Okay. But we can still actually perform some of the operations on these two sets and produce a new set. Okay. So suppose we have an A and we have a B, two sets. Okay. Then we can perform a couple of operations. The first operation is called a union. Okay. And the second operation is called intersection. And then the complement. Okay. Let's take a look at each of the operation. Now, what is a union? Okay. So now the union, to understand the union, if we actually think about two sets, we think about a set as a bag. A set A contains a bag of something, like a bag of rock, for example. B is another bag. Okay. B is another bag, which actually contains a bag of, let's say, how should I? This is rock, and or we can say a bag of plastic box. These two sets has nothing in common, right? It's completely, they have nothing in common. But when we talk about a union, we basically talk about if I mix the elements in these two bags, and that's basically called a union. So, if I mix all these things together, okay, so I put all the rocks and the plastic boxes in the same bucket, then that's the union of these two. Okay, we normally use the notation like a U. Okay, so that's a union of two sets. Now, mathematically, we can define the union in two ways. Okay, now there's one definition, definition one, but we're talking about the same thing. So it's just a different actually wording, different definition. So to make a union of A and B, take all the elements of A and all the elements of B, and the resulting set would be A union B. So that means you mix the elements of both into one bucket. So they're going to create another new set. The new set basically contains the element of A and the element of B. Now, the other one is really like a formal math definition. Okay. So when we define a union of A, we basically means if X is an element of the union of A and B, if and only if X is an element of A or X is an element of B, which is kind of true, right? So, for example, when we have a rocks and the plastic boxes, we mix the rocks and the plastic boxes together, and I pick any element from this union, then it's either a rock or a plastic box, right? So that means if I pick X, which is which is actually the element of the new set A union B, then X is either an element of A or element of B, or could be both. Now the other way is also true. If X belongs to A or X belongs to B, then X belongs to the union. So that's the definition. Okay.
I'm missing the both part, where you say it could be from both.
In this particular case, it's not. In this particular case, it's not.
Okay, thanks.
But, however, if, two sets, they have overlap, when we talk about a union, it could be both. Can you think about this case? Now, this is not a perfect example because we talk about two sets that are disjoint, right? If they're disjoint, if you actually talk about a union of these two disjoint sets, then it's not possible that the element, if element belongs to the union of these two sets, it could be belong to both. But we think about if we're talking about two sets, A and B, so they're overlapping. And then if we union them, we put a union, there's a chance that if element actually belongs to the union, then the element could be belongs to A and the element belongs to B. Does that make sense?
Yes, thank you.
Yeah. So yeah, you're talking about this particular case. That's a special case. So both of these actually can be viewed as a definition for the union. So in that case, if A is a set of birds and B is a set of cat, like the previous case, okay? Then A union B includes all cats and all birds. So in that case, again, this is actually because A and B are disjoint. So, so it could, if any elements in the union, it's either a cat or a bird, cannot be both. Okay. If you know that X is in the union of A and B, then X must be a bird or a cat. Okay, so that's a definition. But in this case, we talk about, so that's the least case. Or basically means X belongs to A, or X belongs to B, or X belongs to both. That could be either case. Okay. Now the second operation between two sets is called intersection. So when we talk about a union, so if we use the diagram, this is set A and this is set B. And the union going to be this, right? It could be include A and the B and also the joint part. Now intersection is kind of we're talking about the the part that belongs to both A and B. Okay, so A intersection B is a notion for A intersection B, and so we also have two definitions. Okay, so to make the intersection of A and B, take only those elements of A and B that belongs to both sets. Okay, and the resulting set would be A intersection B. So now in this case, like the example I just talked about, if one is a set of all rocks, the other one is a set of all plastic box, the intersection should be empty, right? But if we talk about two sets with overlap, then so there are some elements that belongs to both A and B. Like the case, like A is a set of people who can speak English, B is a set of people who can speak French, and then A intersection B basically include the people who can speak both English and French. Okay, they should exclude the people who only speak English or only speak French. Okay, so they have to belong to both. So in this case, you can use the math notation. So when we say A belongs to A intersection B, if and only if A belongs to A and A belongs to B. Okay. So that's the intersection. Now complement. We use the notation A to the C. So A is a notation for complement of A, or A to the C is a notation for complement A. So we use a definition like this. To take a complement of A, take only those elements of a universal set U that are not in A. The resulting set would be a complement of A. Or we can say A, X belongs to the complement of A if and only if X does not belong to A. So we use that notation. That means A belongs to X belongs to A. X is an element of A. But if we say X is not an element of A, we just put the vertical line. Just say as a special case. Okay. Now, if we talk about if A is a set and U is the universal set, so then the rest of the area is the complement of A, right? Now, in a special case, when A is an empty set, that means A does not contain any element. It's an empty set. Then we normally use this a Greek actually character we call a phi to denote the empty set. Now, empty set is also defined as a set, and so then, what is the complement of empty set? The complement of empty set is defined as U, because so if A is actually empty set, then the complement of A, that means everything in the U is a complement of A, right? So we can define these the relationship like this, or the complement of U is empty, either way. Also, if we also can easily see that the A union A complement, this is going to make the whole universal set, right? If we look at this case, A is here, B is A, complement A is here, so they don't actually, they're disjoint set, but they actually make the whole universal set. Okay. Okay, let's summarize this. Okay, so A union B, A intersection B, complement of A, empty set, universal set. A is a subset of B, X is an element of A, and X is not an element of A. So these are all the notations. So we summarize all with this notation. Okay. Now, these are some useful consequences of the definition of the first one is the union. Okay, if A is not an element of A union U, or X union Y, okay, then X is not an element of X, and also X is not an element of U, right? So that's because when you use the definition says if X is an element of X, lowercase x is an element of a capital X and Y, then if and only if X is an element of A or X is an element of Y, right? Now, so that means if X is not an element of U, then X cannot be in X, because if X is in X, then X is an element of X union Y. Or X cannot be in Y, because if X is an element of Y, then X is going to be in element of X in the union Y. So that means if it's X not in union of X and Y, then X cannot be in X, and X cannot be in Y, right? So that's, we can pretty much like prove this by contradiction. Now for the intersection, if X is an element of X intersection Y, then X must be in both X and Y. That also makes sense, right? Because otherwise, if X is not in X, X is not an element of X, and then because by definition, if X is an element of X and Y, that means X is both in X and both in XY. So that's definitely the case. Now, if X is not in a component of X, then X is not in. Oh, sorry, that should be either I just put the A. Let me see what's going on here. Okay, I think this is actually a kind of mistake. How can we correct this? Tell me. If X is an element of X.
If X is an element of A, then X is not an element of A complement.
Yeah. Right. If it's not in the if X is the element of a complement of X, then X is not an element of X, right?
Yes.
I think what you're saying there is X and large X are two different things.
Yeah, that's capital X.
Right.
Yeah.
Right. Right.
So I think I used, I should have used A and B, capital A, capital B. That gonna cause less confusion. But here, X that's a lowercase x. Normally, we use lowercase to represent element. We use capital to represent a set. Okay. Yeah. So, or we can, if I use different notation, I can say if X is actually an element of A, the complement of A, then X is not an element of A. And also if X is not a complement of A, then X is an element of A, right? So this is, but this is definitely confusing because I use X here, I use A here, so this has nothing to do with it. Okay. I'll make a clear correction. Okay. Now I think I'm gonna take a small break, and I leave this actually examples here. So let's actually take a look at this. I will take actually 10-minute break. So please actually look at each of the question and look at the question first, and then answer each of the item here. Answer each of the items here. Okay. So okay, I'll give you 10 minutes. So, and also I need to stop the recording because Google actually don't want, Google doesn't like a long actually file, so I need